Hi, I'm Miss Montguire. Welcome to Astronomy. Today we're going to do a little bit of introductory notes. Sometimes in class we'll do notes in person, and I'll be there to give you detailed instructions. And other times it's just not necessary. Either we'll do a lot of work in class, and so the notes will just be to fill in any gaps you might have, or it's something that you have hopefully a little bit of prior knowledge about, and therefore don't need as much hand-holding in person. So we'll do this video format. Sometimes it'll be during class, maybe a substitute. Other times you'll do it at home. Today, it'll just be to get used to things in class. When we take notes in my class, generally they're guided, which means I'll give you some sort of handout and you fill in what you need. When I do that, typically what you need or the more important information is somehow indicated. Today it's going to be on a color key. So anything that's white is going to be nice to know information. So in other words, write it down if you need to, but otherwise I wouldn't stress about it. The colored information is going to be the stuff that you probably want to know, maybe highlight or make a note of it in your notes. So this is astronomy. Hopefully you know that. Hopefully you're in the right place. And astronomy is essentially the study of space, or more specifically the study of space, celestial objects, and the universe. So let's start with the universe. The universe is essentially everything that exists everywhere. And so it includes, obviously, our planet, but everything beyond our planet, and even the parts where we just can't even really imagine or conceptualize what's out there. That's all considered universe. It's made up of matter, space, and energy. Matter is mostly what you know of as atoms, subatomic particles, things like that. However, there's pretty good evidence to suggest that there's a lot of matter that we can't see that's different than what we understand matter to be. We call that dark matter. There's also energy that works differently than we understand it. We call that dark energy. It basically counteracts what gravity does, at least we think it does. That is kind of like way over anything we're going to cover in class, but just be aware that it's out there. Just a quick note, gravity is the main force, there's other forces, but the main force that holds everything together, including stars and planets. So when we describe the objects in space, often we'll refer to them as celestial objects. We really just mean something in space. Could be a planet, could be an asteroid, a star, a galaxy, really anything that we see. Of course, in astronomy, one of the most important things we're going to talk about is stars, because light mostly comes from stars in space. A star is essentially a hot ball of gas that it's releasing energy because it's undergoing fusion. Fusion is basically taking two small atoms and smushing them together into a bigger atom. Stars can vary greatly. Some are red, some are blue. That varies in size, temperature, even how long they live. Some stars will seemingly exist for all of time, and other stars will fizzle out relatively quickly on an astronomical time scale. One of the other things we'll talk about, and is a component of astronomy, is a solar system. So hopefully you know we live in a solar system. Our planet, Earth, orbits the sun, and so when we refer to our solar system, we mean the sun and all the objects that orbit it, whether the object is a tiny piece of dust or Jupiter, the largest planet. We are, of course, not the only solar system in the universe. Many, many, many stars have their own planets and things that orbit them, and all of them would be considered a solar system or a star system. A planet really has a specific definition that we'll get into later, but essentially it's a very large spherical body that orbits a star, but it's not big enough to do fusion. There's some gray area between some other things that can't do fusion either, but planets is essentially something big that's round and doesn't do fusion. Comets and asteroids are smaller scale. They're typically irregular shaped, as opposed to a planet or a dwarf planet, which is spherical. Moons tend to be smaller things that orbit bigger things. So Jupiter has moons the size of some planets, but they're considered moons because they're orbiting Jupiter. And it doesn't have to be huge to have a moon. Pluto has moons. A number of very small Kuiper Belt objects have moons. So it's just something small that orbits something else. And meteoroids is essentially space debris. It's objects floating around space. Some of it is left over from collisions of asteroids or when the solar system was forming. Some of it's even small as dust particles. Another thing that you might find in the universe is a group of stars. Those groups of stars there's a couple of different names for them. So our star is in what we call a stellar neighborhood. It's essentially saying, hey, Here's our neighborhood. It's 20 light years, and it's everything in that 20 light year range, and we got about 100 stars nearby. Um, Stars are grouped even much larger in star clusters. Those are things that are actually bound by gravity to each other. So perhaps they're orbiting each other or moving as a group around the galaxy. Some of them can be very, very, very large. So groups of stars that are even larger than clusters are galaxies. A galaxy is millions, billions, or sometimes trillions of stars, along with gas and dust between them, that are bound to each other with gravity, meaning once again they move around each other or with each other. And they can have many, many different shapes. Our galaxies, the Milky Way, is spherical. Others of them are considered irregular because they don't really have any defined structure. And some are elliptical, um, and they would be kind of oblong. Our galaxy has about 200 billion stars. It's 100 light years across. And as you see, we're kind of on an outer spoke. This is obviously an artist rendering of our galaxy because we can't get outside of our galaxy to see where we are. But based on calculations, we think we're kind of towards the outside. If you ever heard about the search for habitable planets and where we might look to find life, there's a lot of that going on right now in the news. If this is the entire galaxy, the part we can even see to have any hope of finding a planet is this teeny tiny section right there. So there's a lot in our galaxy that we have no way of finding planets. We can see things like stars that are very bright, but planets, they're just too small and too dark for us to see. When we look at galaxies, here are a couple of different kinds. As you'll notice, we have some irregular shapes, some elliptical shape, and some really cool things. Our galaxy, once again, is thought to be something like this, a spiral galaxy. Even larger than a galaxy is clusters of galaxies. So galaxies have mass and they're attracted to other galaxies. And so we have a local group. So we have a small cluster. Our local group has about 46. We're the second biggest galaxy. And then galaxies are bound to even bigger groups we call superclusters. But a couple things I didn't mention that would be considered in parts of galaxies would be a nebula. A nebula is essentially a cloud of gas and dust. There are different kinds. Some of them are the places where new stars are formed. Others are formed for other reasons. This is the Eagle Nebula, and those are very famous clouds called the Pillars of Creation. And another thing that many of you are probably interested in is black holes. So there's black holes, we think, at the center of galaxies. There's also black holes that form as a star collapses. And so this is Cygnus X1. It's a black hole found in the constellation Cygnus. And we can't see black holes, so this is the only picture we have of it, and it's taken with an X-ray. When we study space, there are a number of different things about astronomy that just makes it unique compared to other sciences. So, for example, we can't go to space and take a scoop of stardust and study it and do experiments on it. We can go to space and do experiments, but we can't really go very far based on all of space, and we can go this tiny distance. And so most of our information we know about space is through observation and modeling, and through comparing what happens on Earth to what we think would happen in space. So, for example, when we look at a star to see what it's made of, we compare the light it gives off to similar light given off by elements on Earth. Studying space also requires new units and ways of gathering and recording data. So obviously we need things like telescope and spectrometers that can measure the light coming from stars. But also we just need new units because the units we have are woefully insufficient when dealing with the humongous numbers we have to measure things in space because the distances and the masses are so large. So to do that, we're going to utilize something that hopefully most of you are familiar with called scientific notation. If you're not familiar with scientific notation, it's okay. I'm going to do a little intro. If you're so confused, come see me. Scientific notation is a way of dealing with either very, very large numbers or very, very small numbers. Most of you most likely encountered it in chemistry, and in that case, you were probably dealing with very, very small numbers. We're going to be doing the opposite. We're going to be dealing with very, very large numbers. For example, this is the Earth's mass. I don't even know how to say that number in like words because it's so large. That, of course, if we were going to do an equation, do some calculations with it, it's just very hard, and most calculators don't even have that many digits. And so to enter it in the calculator, to work with it, or just make it easier, we're going to call it 5.972 times 10 to the 24th. It's still a longer number, but it's by comparison much, much shorter. So what we did is we basically took the first digit and made it a number between 1 and 10, and then multiplied by a number to get it to the right size. So another example that's much easier to work with is Pluto's diameter. The New Horizons spacecraft recently got to Pluto and measured its diameter as 2,370 kilometers. That's a number we don't need anything for because it's nice and easy to work with. But if we were going to turn that into scientific notation, we would take and put the decimal after the first place, so 2.37, and then we'd multiply it by a number that made it into 2,370. In that case, it's 1,000, or 10 to the third. So when we deal with big numbers, essentially we're just moving the decimal point. So in this class, I'm not going to ask you to convert between scientific notation and regular notation. You should have an understanding of it well enough to know which number is larger. So for example, if I gave you 6 times 10 to the 24th, the mass of the Earth, versus 9 times 10 to the 5th, you should know that 6 times 10 to the 24th is a much larger number because the 24th power is way, 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 way bigger than the 9th power. You will also need to know how to enter scientific notation in your calculator. We won't be doing this for a while, so if you're struggling with it, you have plenty of time to come see me. The last thing we're going to talk about in this introduction is the units in space are different. So there are times when the units you've learned in science before, kilometers, meters, kilograms, all work. Kilometers work great for the diameter of planets. So it's a big number, 12,756 kilometers, but it's doable to talk about the diameter of the Earth. Pluto, 2,300 kilometers across, it's a doable number. If, however, we were going to be talking about the distance between planets, kilometers would be a very large number and very difficult to work with. And so astronomers made up a unit to describe the distances within the solar system. So within the solar system, they made up a unit called astronomical units. An astronomical unit is, by definition, the average distance between the Earth and the Sun. So it's just straight out 1. So Venus and Mercury, closer to the Sun, we would expect them to have a number less than 1, which they do. Mars, which is a little bit further away from the Sun than Earth is, has an AU, or an astronomical unit, of 1.52, meaning it is 1.52 times as far from the Sun as Earth is. Another unit that astronomers made up is called a light year. We use it for distances typically outside of our solar system because an astronomical unit is even too small for that. The closest star is 4.2 light years away. That's about 27,000 AU, and that's the closest star. To get to some of the further away ones, Deneb, for example, is really, really far away. It would be just a very large number, so astronomers made up a number called light year, and that is the distance light can travel in a year in a vacuum. So in other words, there's no air resistance it has to encounter. Light can travel, of course, very, very quickly, and so they measured that out, and it's 9.4 times 10 to the 15 meters. That's not important, but it is the distance that light travels. So it is a distance. In Wisconsin, we kind of talk about distances and times a lot. So, for example, I live very near school. It's about 2.5 miles, but when I talk about it to my friends, I say, oh, I only live 7 minutes away. Minutes is a unit of time, but what I mean is it takes me 7 minutes to get there at driving speed. So we're saying that it's a time. So Proxima Centauri, as I mentioned, is our closest star. It's 4.22 light years away. And what it means is that we're just now seeing light emitted from Proxima Centauri that was emitted 4 years, 11 weeks, and 3 days ago. Because Proxima Centauri is 4.2 light years away. The last unit we're going to just mention is called a parsec. Parsec is technically the distance a star must be in order for its observed parallax to be exactly 1. That probably means absolutely nothing to you, and that's okay. We're not going to really get into parsecs. I just wanted to mention it so long as we're talking about units. Parallax is basically a way of measuring angles in order to calculate distance. So if you've taken a trigonometry class or even some of the geometry classes, you know that if you know this angle and you know one of the sides, you can calculate the other side. And so astronomers do that. They can measure the angle and calculate how far away the star is. Because we measure the angle from Earth, it's of course measured in angles. It's not using degrees, it's using a measurement of angle called arcsecond, another reason why we're not using it. But essentially, it's the longest unit of measurement. It's really all you need to know. The last method of measurement we'll discuss today is really more of a comparison than it is an actual unit. So a lot of the time, we don't really need to know the actual number of the mass or the brightness or whatever. We just need to know how the characteristic compares to something we know, like the Earth or the Sun. So, for example, if I'm talking about the size of Jupiter, I might compare it to Earth. Another example would be the star Deneb. The Deneb is a very, very distant star, but we can still see it pretty well because it's very, very large. Its mass is 3.779 times 10 to the 31st kilograms. Well, what does that number mean? Earth is 6 times 10 to the 24th, and they probably just sound like numbers to you. So an easier way of describing it, instead of comparing actual kilogram to kilogram, is to say Deneb's mass is 19 solar masses. In other words, if Deneb has a mass of 19 solar masses, that means it's 19 times more massive than our sun. So this symbol here, the M with a little circle inside of another circle, means solar masses. And so it's just a way of comparing sizes. That's it for our little introduction to astronomy. Let me know if you have any questions.